Hello and welcome to Late Night Cosmos, where the mysteries of the universe unfold under the calming light of the stars. If you're fascinated by the endless wonders of the cosmos, don't forget to like, subscribe, and hit the bell icon so you can join us on more journeys through the vast and infinite universe. Before we dive into tonight's cosmic story, let me know where you're watching or listening from. Are you nestled comfortably at home, gazing up at the night sky, or perhaps imagining yourself drifting across the stars far beyond our world? Wherever you are, I'm glad you're joining us on this voyage. Tonight, we're about to take a peaceful yet awe-inspiring journey through the life cycle of a star. From the quiet birth within cosmic clouds to the fiery finale, each stage is an incredible process of creation, transformation, and ultimately, death. But as we will see, the death of a star isn't an end. It's a dramatic transformation that continues to shape the very fabric of the universe. So, sit back, relax, and let's explore the magnificent, mysterious life of a star. You may just find that, in the end, it mirrors a journey we all must take in the grand scheme of the cosmos. The death of a star is not an end. It is a transformation, one of the universe's most magnificent and powerful processes. To truly understand this transformation, we must first step back and consider the cosmic perspective, as Carl Sagan so eloquently described it. Imagine, if you will, the vastness of the universe stretching out beyond our comprehension. We live on a small rock, orbiting an ordinary star in an unremarkable galaxy. Yet from this tiny speck of dust, we have the ability to peer out and grasp the great drama of the cosmos. Stars are the true architects of the universe. They are cosmic factories, where the raw ingredients of matter are transformed into the very building blocks of everything we know. Hydrogen and helium, the simplest elements, are fused together under the extreme pressures inside a star, creating heavier elements. These elements are released into space when a star dies, seeding the cosmos with the materials needed to create planets, asteroids, and even life itself. In a sense, stars give birth not just to their own successors, but to entire worlds, and to the life that might one day thrive on them. Fred Hoyle, the British astrophysicist, played a key role in our understanding of this process. He proposed the theory of stellar nucleosynthesis, which explains how stars create heavier elements through nuclear fusion. Without stars, there would be no carbon, no oxygen, no iron, the very elements essential for life. It was in the heart of these stellar furnaces that the ingredients for life were forged, creating the complex molecules that would one day find their way to Earth and elsewhere in the universe. The death of a star, especially the most massive ones, is where the story becomes truly fascinating. As stars run out of fuel, they begin to undergo dramatic changes. But their death isn't just about the collapse of a dying body. It's an event that can give rise to something entirely new. For instance, when a massive star exhausts its nuclear fuel, its core contracts and becomes so dense that it triggers a supernova explosion, a blast so bright it can briefly outshine an entire galaxy. The explosion scatters the elements created inside the star across space, enriching the cosmic material from which new stars, planets, and even life can emerge. We owe much of our understanding of stellar evolution to scientists like Margaret Geller, who helped shape the study of cosmic structures and galaxy formation. Geller's work, particularly her contributions to mapping the distribution of galaxies, revealed how stars, galaxies, and entire cosmic structures are interconnected, giving us a deeper understanding of how the death of stars contributes to the growth and evolution of the universe on a grand scale. Stars are not solitary actors in the cosmic drama. They are part of a grand interconnected cycle. Their birth, life, and death are all part of a larger process of creation, destruction, and renewal. Each star's death, whether it results in a white dwarf, neutron star, or black hole, influences the universe in profound ways, shaping the very material that will form the next generation of stars and planets. In a sense, stars live on through their remnants, continuing to shape the universe long after their light has faded. This cycle, driven by the deaths of stars, gives rise to more than just the physical materials needed for new stars and planets. It opens the door to the possibility of life, as the elements forged in the hearts of stars become the essential ingredients for the molecules of life. And in this way, the death of a star is not just an event, it is part of a much larger, ongoing process of cosmic evolution that is still unfolding. The transformation of a star, its birth, its life, and its eventual death is a story that speaks to the very nature of the universe itself. It is a story of change, of cycles that are eternal and ever-renewing, and of the incredible forces that govern the cosmos. As we explore the life cycle of stars from their birth in cosmic clouds to their fiery demise, we begin to understand how intimately tied the death of a star is to the creation of new life, both in the universe and on the planets that orbit the stars. A star begins its life not with a flash of light, but with a slow, quiet gathering of cosmic material. Long before the star shines, there is only cold, primordial gas, particles drifting in the emptiness of space, remnants of the Big Bang itself. This gas, mostly hydrogen, is the raw material from which all stars are born. It might surprise you to know that this gas has been drifting through the cosmos for billions of years, its journey shaped by the forces of gravity and the universe's grand design. The story starts with what is called the nebula theory, an idea first proposed in the 18th century by Immanuel Kant and Pierre-Simon Laplace. It tells us that stars form from clouds of gas and dust. This theory has stood the test of time, but modern science has added layers of complexity to our understanding of how these gas clouds come together to form stars. One of the most important factors in this process is dark matter. You might have heard of dark matter before, and while we can't see it directly, we know it exists because of the way galaxies move. Adrian Jenkins, a prominent astrophysicist, has done groundbreaking work simulating the role of dark matter in star formation. His simulations suggest that dark matter doesn't just sit quietly in space. Instead, it forms large clumps, called galactic halos, that exert an invisible gravitational pull. These halos are crucial because they help to funnel gas into certain regions of space, where it condenses and begins to form stars. Without the influence of dark matter, star formation might look very different and much slower. But it's not just the gas from the Big Bang that shapes the birth of stars. Maurice de Haan, a physicist with a unique perspective, introduced the idea of fossil gas. This hypothesis suggests that the gas clouds that form new stars aren't always entirely fresh. Some of the gas comes from ancient long-dead stars. These fossil clouds might be remnants of stars that died in distant epochs, and they carry with them the chemical signatures of previous generations. In this way, gas clouds that eventually collapse into new stars are not merely recycled, they are a cosmic inheritance carrying with them the history of the stars that came before. And just when you think it couldn't get more interesting, there's the role of magnetism in all of this. Often overlooked in classical models, magnetic fields play a surprisingly vital part in star formation. Rainer Beck, a leading researcher in this field, has shown that magnetic fields are not just passive background players in star formation, they actively shape the process. Magnetic fields can slow down or speed up the collapse of gas clouds. They create turbulence and stir the gas in ways that lead to the formation of dense clumps of matter, which under the right conditions become stars. The influence of magnetic fields in molecular clouds, where stars are born, has fundamentally changed our understanding of how these stellar nurseries work. All of these elements, dark matter, fossil gas and magnetic fields, create the conditions for star formation. But at the heart of it all is gravity. Gravity, the force that binds everything in the universe together, is the key player. As gas clouds begin to collapse under their own weight, they grow denser and hotter. Eventually, the pressure becomes so great that nuclear fusion begins, the process that powers stars. Hydrogen atoms are fused together, forming helium and releasing vast amounts of energy in the form of light and heat. This marks the birth of a new star, a fiery furnace of energy and light. But how does all of this fit into the bigger picture of the universe? Well, the birth of stars isn't just a random process. It's intimately tied to the structure of the universe itself. The work of scientists like James Peebles has helped us understand how large-scale structures in the universe, such as galaxies and clusters of galaxies, are influenced by the distribution of matter, both visible and invisible. Peebles' work in cosmology has provided a framework for understanding how the birth of stars is part of the larger process of cosmic evolution. The way stars form, live, and die is intricately connected to the shape and movement of galaxies, and ultimately to the very fabric of space-time itself. So, from the primordial gas left over from the Big Bang to the quiet influence of dark matter, stars are born in a process that is much more complex and interconnected than we once thought. Their birth is a cosmic event, one that stretches across billions of years and connects the past to the future. As we move through this journey, we'll see how these stars will live, how they'll change, and how their death will fuel the next generation of stars, planets, and perhaps even life. As a star enters the main sequence of its life, it reaches a delicate balance, one that is maintained for most of its existence. This balance between gravity pulling inward and the energy from nuclear fusion pushing outward forms the backbone of the star's stable, glowing existence. You could think of it like a cosmic tug-of-war, with these two opposing forces constantly in play, ensuring the star neither collapses in on itself nor explodes outward. At the core of this equilibrium is nuclear fusion, the process by which stars generate energy. In the early stages of a star's life, its core is composed primarily of hydrogen. Through fusion, hydrogen atoms combine to form helium, releasing vast amounts of energy in the process. This energy radiates outward, creating the light and heat we see coming from the star. It's this outward radiation pressure that pushes against the force of gravity, trying to pull everything inward, keeping the star stable. This balance between the inward pull of gravity and the outward push of fusion energy is the hallmark of a star in the main sequence phase. But the relationship between fusion and gravity is not as simple as it might first seem. Sir Arthur Eddington, a pioneering British astrophysicist from the early 20th century, played a crucial role in understanding this balance. He discovered what we now call the mass-luminosity relation, which explains how the amount of light a star produces is directly related to its mass. Larger stars burn brighter, but they also burn their fuel more quickly. Smaller stars, on the other hand, burn less brightly and live longer, maintaining their balance for billions of years. Eddington's work focused on how a star's luminosity, or brightness, is determined by the pressure at its core. This pressure, driven by the energy produced by fusion, must balance the gravitational force trying to collapse the star under its own weight. Eddington's equation, L equals m to the power of 3.5, showed that the luminosity of a star is proportional to its mass raised to the power of 3.5. This simple yet profound relationship helped define how stars live, grow, and eventually die, and it still guides much of our understanding of stellar dynamics today. However, while Eddington's work laid the foundation for understanding stellar behavior, modern astrophysics has expanded these ideas in exciting new directions. For example, Michael Turner, a renowned cosmologist, has introduced ideas about dark energy's influence on stars and their evolution. Turner suggests that dark energy, which is responsible for the accelerated expansion of the universe, may also play a subtle role in stellar evolution on larger scales. Although dark energy's influence is far more apparent in the expansion of galaxies and the cosmos as a whole, its indirect effects on individual stars may influence their life cycle, particularly as we consider the behavior of stars in galactic environments over vast cosmic timescales. This new perspective expands our understanding of the universe beyond what we see. Stars, after all, are not isolated entities. They exist within galaxies, which are influenced by the mysterious force of dark matter. While dark matter doesn't interact with light, we know it exists because of its gravitational effects on visible matter. Vera Rubin, an astronomer who made groundbreaking contributions to our understanding of dark matter, observed how galaxies spin. She found that the outer regions of galaxies were moving much faster than expected, indicating the presence of unseen mass. Rubin's observations revealed that dark matter exists in large quantities, and it is deeply intertwined with the gravitational forces that shape galaxies. What's fascinating is that dark matter, although invisible, is thought to play an important role in the formation and life cycles of stars. In fact, it might influence the gravitational environment around stars, affecting how they're born, evolve, and die within their galaxies. So, the presence of dark matter in a galaxy could indirectly affect the dynamics of a star's life, adding another layer of complexity to the main sequence phase. And if we look even deeper into the workings of the universe, beyond the classic models of star formation and life cycles, some researchers, like Gerald Cleaver, have introduced fascinating ideas about how the universe itself operates at the most fundamental level. Cleaver, with his holographic universe approach, suggests that the structure of the universe at the quantum level, the smallest scale of reality, could influence the behavior of stars in ways we haven't fully appreciated. According to this theory, the universe is not just a three-dimensional space, but has a deeper underlying structure that is reflected in the processes we observe in stars. Cleaver's hypothesis is rooted in the idea that at the quantum level, the universe may function more like a hologram, with information being encoded in ways that we cannot easily detect with our current understanding of physics. If this is true, then the fundamental processes of star formation and evolution could be tied to a much broader, more complex cosmic blueprint. This line of thinking challenges us to reconsider what we know about the fundamental forces at play in stars, and how the balance of gravity and fusion might not just be a local, star-specific phenomenon, but part of a deeper, universal pattern. In this light, stars are not just individual burning furnaces, they are interconnected with the very fabric of the cosmos itself. Their stability, their fusion processes, and even their eventual death might be influenced by the larger forces of dark energy, dark matter, and the quantum structure of the universe. As we peer deeper into the life cycle of stars, we may find that the secrets of their existence stretch far beyond the core of each star, reaching into the very nature of the universe's grand design. Stars, it turns out, are far more than just the bright points of light we see in the night sky. They are the product of cosmic forces, both known and unknown, and they hold the key to understanding not just how galaxies form, but how the universe itself evolves. Their birth, their balance, and their eventual death are all part of a larger cosmic process that stretches from the smallest quantum scale to the vast expanding universe around us. The more we understand the balance between gravity and fusion in a star, the more we uncover about the universe's deepest mysteries. And this journey into stellar evolution is just beginning. As stars evolve, their cores go through remarkable changes, shifting from hydrogen to helium and eventually to even heavier elements. This transformation marks a pivotal moment in the life of a star, and it's a process that reveals the true complexity of stellar physics. While most people think of stars as simply burning hydrogen to produce helium, the reality is much more intricate. As stars age, their internal structures become increasingly dynamic, with convective zones and complex fusion cycles coming into play. When a star exhausts the hydrogen in its core, it begins the next phase of its life, the red giant phase. This is a period of dramatic change. With hydrogen no longer available to fuel the core, the star's center begins to contract under the weight of gravity, increasing in temperature and pressure. Meanwhile, the outer layers expand and the star grows in size, becoming a red giant. But this expansion isn't just about getting bigger. It signals that the star is about to shift from one fusion process to another. At this point, helium becomes the new fuel. The core of the star, now much hotter and denser, begins fusing helium into heavier elements like carbon and oxygen. This process, called helium fusion, generates even more energy, which pushes outward against the force of gravity. But as stars transition into red giants, their cores behave in surprising ways, much like a fluid system. Peter Goldreich, a respected astrophysicist, proposed that stars in this phase are not just simple fusion reactors. Instead, they behave like fluid systems in which convection plays a crucial role. Goldreich's theory of convective instability suggests that the energy generated in a star's core doesn't just radiate outward in a smooth, orderly way. Instead, the core undergoes convective motions. Essentially, hot gas rises and cooler gas sinks, creating a turbulent, fluid-like behavior inside the star. This convection is responsible for mixing the star's inner layers, distributing heat and matter in a way that supports the ongoing fusion process. In other words, the interior of a red giant behaves more like a boiling pot of soup than a calm furnace. This convection is vital for the star's ability to continue fusing elements and sustaining its energy balance. But the story doesn't stop at helium fusion. In massive stars, the quest for heavier elements continues, creating an even more complex environment. As the core of the star becomes rich in helium, the temperature and pressure eventually rise enough to trigger the fusion of heavier elements, like carbon and oxygen. But something even more fascinating happens in very large stars, where fusion and fission processes intermingle in what's called a fission-fusion cycle. Luca Giallanella, an astrophysicist exploring this idea, suggests that in the extreme environments of large stars, both fusion and fission could occur simultaneously, in a kind of cosmic dance. Fusion, as we know, involves lighter elements combining to form heavier ones, releasing energy in the process. But in certain conditions, like those found in a dying star's core, fission processes, where heavy elements split apart, can also take place, releasing energy. This fission-fusion cycle adds another layer of complexity to the life cycle of a star, particularly in its final stages before it undergoes a supernova explosion. As these stars fuse heavier elements, they begin to create elements that are crucial for life itself. The formation of carbon, oxygen, and other elements is not just a random process, it's a cosmic necessity. The work of Alistair Gunn has shed light on how neutron capture processes, which occur in the most extreme environments of stars, create these elements. Gunn's theoretical models explain how the intense radiation in a star's core can cause neutrons to interact with atomic nuclei, creating heavier elements through a process known as nucleosynthesis. This neutron capture, particularly in the late stages of a star's life, creates the elements that eventually make their way into space, enriching the universe with the building blocks of life. When we consider the broader implications of these processes, we realize that stars aren't just nuclear reactors, they are factories for the universe. The elements that make up everything we know, planets, life, even the air we breathe, were forged in the hearts of stars. The death of a star, particularly a massive one, is not just the end of a life, but the beginning of a new chapter in the cosmic story. The materials created through fusion and fission cycle through the universe, contributing to the formation of new stars, planets, and perhaps even new forms of life. As stars expand into red giants, their internal processes become more complex, not only because they're fusing heavier elements, but also because they are participating in a much larger interconnected cosmic system. The convection in their cores, the fusion and fission cycles, and the creation of essential elements all play a role in shaping the next generation of stars and galaxies. These processes are not confined to just one star, but are part of the grander narrative of the universe, where every star contributes to the cosmic ecosystem. From the birth of the first stars which emerged from the primordial gas of the Big Bang, to the eventual deaths of these stars which scatter elements across the universe, we see a cosmic cycle that has been unfolding for billions of years. The death of each star is part of a larger ongoing process of creation, destruction, and rebirth. An eternal rhythm that shapes the very fabric of the universe. In the end, red giants are not just the grand, swollen remnants of stars. They are the heart of a much larger cosmic story of transformation. Every shift in their internal processes, from the fusion of hydrogen to helium, and then to heavier elements, is a crucial step in the creation of the universe as we know it. As a massive star nears the end of its life, the delicate balance that sustained it for millions or even billions of years begins to collapse. This process is nothing short of cosmic drama, an intricate dance between gravity and fusion, where gravity ultimately wins. The result is the internal collapse of the star, an event that leads to one of the most energetic explosions the universe can produce, the supernova. This violent death not only marks the end of the star's life, but also gives birth to the stellar remnants that will shape the future of the galaxy. When a star reaches the end of its hydrogen fuel, it begins fusing heavier elements in its core. The core contracts under the force of gravity, while the outer layers expand. As the core becomes enriched with heavier elements like carbon, oxygen, and eventually iron, the fusion process slows down. Iron, unlike lighter elements, cannot release energy through fusion. This marks the point at which fusion can no longer support the star against gravity, and the star begins to collapse inward, unable to sustain itself any longer. It is in this moment of collapse that the star's fate hangs in the balance. The core, now under immense pressure, reaches temperatures of tens of billions of degrees. Gravity continues to compress it, and the density increases beyond imagination. For a brief fleeting moment, the core is so hot and dense that it becomes a crucible of unimaginable forces. During this collapse, the star's outer layers are violently thrown outward in what is known as a Type II supernova. This catastrophic event is an incredibly energetic release, one that outshines an entire galaxy for a short period of time. But what exactly causes this explosion, and why does it release so much energy? Robert P. Kirshner, an astrophysicist known for his work on stellar explosions, explained that the Type II supernova occurs when the core of the star, primarily composed of iron, becomes unstable and collapses rapidly. The process is initiated by the collapse of the iron core, which cannot sustain itself through fusion. When the core contracts, it eventually reaches a point where the density becomes so high that the protons and electrons combine to form neutrons. This sudden transformation generates a shock wave, which causes the outer layers of the star to explode outward, releasing an incredible amount of energy. Kirshner's studies on supernovae energy output highlight how these explosions are crucial for dispersing heavy elements such as iron into space, seeding the formation of new stars and planets. However, the explosion is not simply an ordinary release of energy. It's much more complex, involving high-energy particle physics and the role of neutrinos, particles that are famously difficult to detect but carry a vast amount of energy. John Conway, a physicist with an interest in high-energy particle physics, explored the role of neutrinos in stellar collapse. Neutrinos, though elusive, play a key role in the energy dynamics of a supernova explosion. During the collapse, a large amount of energy is carried away by neutrinos, which interact with the surrounding material, contributing to the shock wave that ultimately blows the star apart. In fact, the neutrinos are so energetic that they can account for up to 95% of the energy released during a supernova. Without them, the star's outer layers might not have the energy required to explode. But the tale of stellar death doesn't end with the explosion itself. In some cases, the destruction of a star leads to what could be called a cosmic cannibalism. Shmuel Bialy, an astrophysicist, has proposed a fascinating theory about the possibility of star cannibalism. According to Bialy's hypothesis, when a star dies, particularly in the case of massive stars, it can be engulfed by a giant molecular cloud. These clouds, made up of dense gas and dust, can consume the dying star, accelerating its collapse. This can have profound effects on the star's final stages, potentially altering the way it explodes and the types of remnants it leaves behind. Bialy's theory adds another layer of complexity to the process of stellar death, suggesting that star formation and star death are not always separate events but can be deeply intertwined. While the supernova explosion scatters vast quantities of matter into space, the remnant left behind can be equally fascinating. For stars with enough mass, the core that remains after the explosion can collapse further, leading to the formation of a neutron star, or, in the most extreme cases, a black hole. These remnants are incredibly dense, packing the mass of several suns into a space smaller than a city. The physics at work in these remnants is extraordinary, and it's not just a simple collapse of matter. Instead, it's a process that challenges our understanding of matter, space, and time itself. George Gamow, a physicist famous for his work in nuclear theory, made important contributions to understanding the behavior of stellar material under extreme conditions. Gamow's work on the liquid drop model, which was originally applied to nuclear fission, provides an interesting way of thinking about how material behaves under the intense pressure of a collapsing star. In this model, the core of the star behaves like a liquid drop, where the intense forces at play distort the material and cause it to collapse into a denser form. This approach helps explain how a star's core can reach such extreme densities and temperatures, ultimately leading to the formation of neutron stars and black holes. Gamow's ideas have provided a fresh angle on how stellar material interacts under such intense conditions, contributing to our understanding of stellar collapse and the formation of stellar remnants. The death of a star is not just an end, it's the beginning of something new. The elements created in the star's core are scattered across space, enriching the interstellar medium and contributing to the formation of new stars, planets, and even life. The energy released in the explosion helps drive the dynamics of galaxies, influencing star formation rates and the overall evolution of the cosmos. From the collapse of a star's core to the shock wave that disperses heavy elements, every moment of a supernova is a key piece of the universe's ongoing cycle of creation and destruction. As we reflect on the death of a massive star, we can appreciate how these events are not simply catastrophic explosions. They are transformative moments in the life of the universe, moments that create the raw materials for future generations of stars and planets. The complexities of stellar death, from the role of neutrinos to the possibility of star cannibalism, reveal just how intricate and interconnected the universe truly is. What may seem like the end of a star's life is actually a new beginning, one that continues to shape the cosmos in ways we're only beginning to understand. When a massive star reaches the end of its life, its core collapses under the immense force of gravity, creating one of the most fascinating and extreme objects in the universe, a neutron star. These remnants of stellar death are incredibly dense, where the matter inside them is compressed to such an extent that protons and electrons combine to form neutrons. The result is an object with a mass greater than that of the Sun, yet squeezed into a sphere only about the size of a city. The densities involved are almost beyond comprehension, and the forces at play within neutron stars challenge our very understanding of matter itself. At the heart of the neutron star's extraordinary density lies a phenomenon known as neutron degeneracy pressure. This is the force that prevents the neutrons in the star from collapsing any further. The physics behind this force comes from the Pauli exclusion principle, which states that no two particles can occupy the same quantum state at the same time. For neutrons, this principle creates a kind of pressure that resists further compression, stabilizing the star against the inward pull of gravity. Without this degeneracy pressure, the neutron star would collapse into something even more compact, perhaps a black hole. It's this delicate balance between gravity and neutron degeneracy pressure that allows a neutron star to exist. The physics of neutron stars is not just confined to the behavior of matter at high densities. There are still many aspects of their formation and structure that are not fully understood. One fascinating area of study is the role of neutrinos in neutron star formation. Neutrinos are subatomic particles that interact very weakly with matter, making them incredibly difficult to detect. However, their role in stellar collapse and neutron star formation is crucial. David N. Klein, a physicist known for his work on neutrinos, has explored how these particles might contribute to the overall dynamics of neutron star formation. When a massive star's core collapses, neutrinos are released in vast amounts, carrying away a tremendous amount of energy. This energy loss is essential to the formation of a neutron star, as it helps the collapse reach the extreme densities needed for neutron degeneracy pressure to take hold. In addition to their role in stellar collapse, neutrinos may also provide clues about some of the universe's most mysterious phenomena. Jim Peebles, a renowned cosmologist, has speculated that the quantum structure of neutron stars could hold the key to understanding dark matter. Dark matter, the invisible substance that makes up most of the mass in the universe, has never been directly observed, yet its presence is inferred from its gravitational effects on visible matter. Peebles' work suggests that neutron stars with their extreme conditions could provide insights into the fundamental nature of dark matter. The interactions between neutrinos and the dense matter in neutron stars could reveal information about the composition of dark matter, offering a tantalizing connection between neutron stars and some of the biggest mysteries of cosmology. Neutron stars are not just dense, compact objects. They also possess some extraordinary properties that challenge our understanding of how matter behaves under extreme conditions. For example, within the core of a neutron star, the density is so high that atoms are crushed into a state where they no longer resemble the atoms we encounter in everyday life. Instead, they form a kind of soup of neutrons, with a small number of protons and electrons scattered within. This extreme density gives rise to strange and powerful phenomena, one of which is superfluidity. Superfluidity refers to a phase of matter in which it flows without viscosity, meaning it can move without losing energy. In the incredibly dense core of a neutron star, some of the neutrons can enter a superfluid state. This phenomenon was explored by physicists like Anderson, Komma, and Janyuk, who studied the behavior of superfluids inside neutron stars. They found that the superfluid neutrons in the star's interior could have a significant impact on the star's overall dynamics. For example, superfluid neutrons might allow for the transfer of energy and angular momentum within the star, affecting how the star spins. These findings challenge our traditional understanding of how matter behaves in extreme conditions, showing that neutron stars are far from simple objects. Neutron stars also rotate incredibly rapidly. Some spin hundreds of times per second. This rapid rotation can cause the star to emit beams of radiation from its magnetic poles, creating what we observe as a pulsar. Pulsars are neutron stars that emit regular pulses of radiation, and they serve as cosmic lighthouses, flashing their beams across the universe. These pulses are incredibly regular, making pulsars excellent cosmic clocks. The study of pulsars has helped scientists test theories of relativity and has provided insight into the extreme physics of neutron stars. But while neutron stars are fascinating on their own, they are also important for understanding the larger universe. The intense magnetic fields and rapid rotation of pulsars can have a significant impact on their surroundings. For example, when a neutron star is part of a binary system, it can interact with its companion star in dramatic ways. The gravitational pull of the neutron star can strip material from its companion, forming an accretion disk. As the material spirals toward the neutron star, it heats up, emitting X-rays. These interactions are not just interesting in their own right. They also provide important information about the behavior of matter under extreme conditions and contribute to our understanding of the evolution of compact objects in the universe. Neutron stars also play a critical role in the broader cosmic cycle. When two neutron stars collide, the result is a cataclysmic event known as a kilonova. The collision of these dense objects generates an explosion that produces heavy elements like gold and platinum, which are then spread throughout the universe. This process is thought to be one of the main sources of these precious metals in the universe, underscoring the importance of neutron stars in the creation of elements that make up planets and even life itself. The extreme physics of neutron stars, their density, rotation, and magnetic fields, provide a window into the behavior of matter at the most fundamental level. Neutron degeneracy pressure, the role of neutrinos, the superfluidity of neutrons, and the study of pulsars all reveal a complex and interconnected system of forces at play inside these enigmatic objects. Furthermore, neutron stars may hold the answers to some of the deepest mysteries in physics, from dark matter to the behavior of matter under the most extreme conditions. As we continue to study neutron stars, we not only gain a better understanding of stellar evolution, but also uncover new clues about the very nature of the universe itself. The journey into the heart of a neutron star is, in many ways, a journey into the heart of the cosmos. When we think of the most extreme objects in the universe, black holes often come to mind, but there is another class of stellar remnants that is just as fascinating, if not more so: magnetars. These unusual and powerful neutron stars are unlike anything we experience on Earth. Magnetars are neutron stars with magnetic fields so strong they can warp space around them, affecting the very fabric of their surroundings. Their magnetic fields are billions of times stronger than the strongest fields we encounter in everyday life. To put that in perspective, the magnetic field of Earth is about 50 microteslas, while a magnetar's magnetic field can reach up to 100 trillion teslas, an incredibly immense and mind-boggling number. Magnetars are formed in much the same way as other neutron stars, following the collapse of massive stars. However, what sets them apart is their intense magnetic fields. The process that generates these fields is not entirely understood, but one prevailing theory is that during the collapse of the star's core, the conservation of angular momentum and the extreme compression of matter generate a magnetic field that is exponentially amplified. This amplification creates fields that are so powerful they can distort space itself, producing fascinating and extreme phenomena. One of the most striking features of magnetars is their unique X-ray emissions. Unlike typical neutron stars, which are often observed as pulsars emitting regular bursts of radiation, magnetars flare with intense bursts of energy that can last from milliseconds to hours. These flares release more energy than the sun does in a year in just a few moments. This extraordinary behavior led to a groundbreaking study by astrophysicist Luigi Stella, who first proposed that these bursts of X-rays were a result of the magnetar's extreme magnetic field interacting with the surrounding plasma. Stella's work changed the way we think about neutron stars, showing that magnetars are not merely dead remnants of stars, but dynamic, active objects with incredible energy at their cores. However, the story of magnetars doesn't stop there. To understand their true complexity, we need to take a look at the behavior of their magnetic fields, and here, Hélène Le Guillau's fractal theory provides an intriguing new perspective. Le Guillou, a physicist known for her work in complex systems, applied her theory of fractals, patterns that repeat at every scale, to the magnetic fields of magnetars. According to her theory, the magnetic field in a magnetar is not uniform, but is instead made up of fractal patterns, with energy distributed in a self-similar way across multiple scales. This idea is revolutionary, because it suggests that the energy in magnetars' magnetic fields doesn't just emanate from a single point, but is distributed across a vast range of scales, creating the potential for the magnetic field to influence surrounding space in much more profound and complex ways than previously thought. This fractal energy distribution could be responsible for the irregular and unpredictable bursts of radiation that magnetars emit, as well as the way their magnetic fields interact with nearby matter. But magnetars might play a role that goes beyond just their immediate environment. Giovanni Fabiano, an astrophysicist, has proposed a fascinating theory that magnetar flares could be linked to the large-scale dynamics of galaxies themselves. Fabiano's hypothesis suggests that the energy released in a magnetar's flares could have a significant impact on the evolution of its host galaxy. These flares, which can release enormous amounts of energy, could influence the rate of star formation in the galaxy. They might help regulate the interstellar medium, the gas and dust between stars, by heating it up and preventing gas from clumping together to form new stars. Essentially, magnetars could act as cosmic regulators, shaping the future of star formation on a galactic scale. This idea challenges traditional views, suggesting that rather than being isolated objects, magnetars might play a crucial role in the overall evolution of galaxies. Magnetars are also interesting because of their complex theoretical structure, one that has opened new avenues for astrophysics. Pavlos Virtalaskos, a physicist specializing in unconventional magnetism, has expanded on the understanding of magnetars by proposing that their magnetic fields could be tied to unknown cosmic phenomena. Laskos' work looks at the magnetic properties of these stars from a perspective that goes beyond conventional electromagnetism. He suggests that the behavior of magnetars could be linked to yet undiscovered aspects of the universe's fundamental forces. This exploration of unconventional magnetism opens up exciting new possibilities for how we understand not just magnetars, but the larger cosmic forces that govern stellar evolution. Through these investigations, we begin to see magnetars in a new light, not just as strange remnants of massive stars, but as dynamic, energy-rich objects that may have a much broader impact on their surroundings. They may hold the keys to understanding not only the most extreme aspects of stellar evolution, but also some of the deepest mysteries of the universe itself. For example, the extreme magnetic fields of magnetars may hold answers to questions about the behavior of matter under conditions we can't replicate on Earth. In these environments, matter behaves in ways that challenge our understanding of physics. The interactions between the magnetic field and the surrounding plasma inside a magnetar are so intense that they could reveal new properties of matter and energy. This could have implications for everything from the study of high-energy physics to the understanding of exotic states of matter, such as quark-gluon plasma, which exist only under the most extreme conditions. Magnetars also offer a glimpse into the future of astrophysical research. The study of these stars has already led to the development of new theories in high-energy astrophysics, magnetism, and even quantum mechanics. As our tools and methods improve, we are likely to uncover even more about these cosmic objects and their place in the universe. Magnetars, with their extreme magnetic fields, erratic flares, and potential connections to galactic evolution, are no longer just curiosities of the universe. They are a key to unlocking some of the most profound mysteries about the nature of the cosmos itself. In the end, magnetars are not just stars that shine briefly and fade. They are stellar beacons of extreme magnetism, complex in their structure and profound in their potential to shape the universe around them. With every flare and every pulse of radiation, they remind us that the universe is full of phenomena far stranger and more beautiful than we could ever have imagined. And as we continue to study these cosmic marvels, we may find that the secrets they hold could revolutionize our understanding of the universe at its most fundamental level. When a massive star reaches the end of its life, it may not simply fade away. It may undergo a spectacular collapse that gives birth to one of the most mysterious and extreme objects in the universe, a black hole. This dramatic transformation is the result of a battle between gravity and all the forces trying to prevent collapse. Gravity wins. When a star's core becomes so dense that nothing, neither light nor matter, can escape, a black hole is formed. At the heart of this phenomenon lies the singularity, a point in space where matter is crushed to an infinitely small volume, and the laws of physics as we know them break down. The singularity is often described as the heart of the black hole, a region where gravity becomes so intense that space and time themselves are warped beyond recognition. According to the theory of general relativity, developed by Albert Einstein in the early 20th century, the singularity represents a point of infinite density. But this is not just a theoretical curiosity, it represents the extreme limit of the forces of nature, where everything we understand about the universe breaks down. In addition to the singularity, black holes are defined by the event horizon, the boundary beyond which nothing, not even light, can escape. Imagine it as the point of no return. If anything crosses this boundary, it is irreversibly drawn into the black hole, where the laws of physics no longer seem to apply in any way that makes sense to us. This point of no return is where many of the most intriguing questions about black holes arise. What happens when something crosses the event horizon? Can anything escape from it? And what exactly lies within the singularity? The nature of black holes has captivated physicists and astronomers for decades. Roger Penrose, a renowned British physicist, made major contributions to our understanding of singularities. He showed that the formation of singularities is not just a mathematical oddity, but a natural outcome of the laws of general relativity. Penrose's work introduced the concept of gravitational collapse. The idea that a star's core, once it can no longer support itself through nuclear fusion, will inevitably collapse under its own gravity, leading to the formation of a black hole. In the 1970s, the legendary physicist Stephen Hawking expanded our understanding of black holes by introducing the concept of Hawking radiation. This groundbreaking theory suggests that black holes are not entirely black. Due to quantum mechanical effects near the event horizon, black holes can emit radiation and lose mass over time. This radiation, known as Hawking radiation, is emitted as pairs of particles that spontaneously pop into existence at the event horizon. One of these particles falls into the black hole, while the other escapes into space. Over time, this radiation causes the black hole to lose mass and energy, eventually leading to its evaporation. Though Hawking's theory has not yet been directly observed, it provides a compelling picture of black holes as dynamic objects that evolve over time, rather than static points of no return. While these classical theories of black holes have been transformative, there are still many unanswered questions, especially when it comes to the larger role black holes might play in the universe. One of the more speculative and controversial ideas is cosmological natural selection, a theory proposed by physicist Lee Smolin. Smolin's theory suggests that black holes could act as portals to new universes. He argues that each time a black hole forms, it could create a new universe in which the physical constants, such as the strength of gravity or the charge of the electron, might differ from those in our universe. This process would be similar to natural selection, where universes that have properties conducive to the formation of black holes would be more likely to survive and produce more black holes. In this view, black holes may not just be the end of a star's life, they may be the beginning of a new cosmic cycle, where the birth of a new universe follows the death of an old one. This idea offers an entirely new perspective on the role of black holes in the cosmos. Rather than being the final stage of a star's life, they could be seen as the gateways to new universes, perpetuating an endless cycle of cosmic creation. The implications of Smolin's theory are far-reaching and have profound consequences for how we think about the universe as a whole. If true, this would mean that black holes could be the key to understanding the true nature of our own universe and the possibility of a multiverse, a vast collection of parallel universes, each with its own set of physical laws and constants. Another intriguing concept is the idea of quasi-black holes, proposed by Carlos Castro Perelman. Perelman's hypothesis introduces an intermediate state between neutron stars and black holes, an object that is not quite a black hole, but still possesses some of the defining characteristics of one. These quasi-black holes would be stellar remnants with incredibly high densities, but without a complete event horizon. Perelman suggests that these objects might have been overlooked in the past, and that they could occupy an important middle ground between the known phenomena of neutron stars and black holes. The discovery of such objects could revolutionize our understanding of stellar evolution and the final stages of massive stars. When thinking about the potential for utilizing black holes in the future, the ideas of Nikolai Kardashev, a Russian astrophysicist, come into play. Kardashev is best known for his work on the Kardashev scale, which measures the level of technological advancement of a civilization based on its energy consumption. Kardashev proposed that a Type 1 civilization, which harnesses the energy of its planet, could eventually evolve into a Type 2 civilization, one that harnesses the energy of its entire star. But what about a Type 3 civilization? Kardashev speculated that a civilization at this level could capture and use the energy from black holes themselves. The power that a black hole's accretion disk, where matter is drawn into the black hole, releases could potentially be harnessed, providing unimaginable amounts of energy for a technologically advanced society. Imagine a civilization capable of controlling the energy of a black hole. This might sound like science fiction, but the study of black holes and their extreme environments could one day open the door to new technologies that we can barely begin to imagine. The energy from a black hole's accretion disk could be enough to power entire star systems, and the possibility of harnessing such energy could one day revolutionize space exploration and power generation on a cosmic scale. The formation of black holes marks the death of a star, but the story does not end there. These mysterious objects play a crucial role in the universe's grand design, potentially serving as portals to new universes, driving the evolution of galaxies, and offering possibilities for future civilizations to harness their immense energy. From the singularity at their core to their potential role in cosmological natural selection, black holes are not just the end of a star's life. They are part of a larger, ongoing cosmic process that may one day help us answer the most profound questions about the nature of the universe itself. As we continue to study black holes, we may find that they hold the key not just to understanding the death of stars, but to the very origin and future of everything. Black holes are among the most mysterious and puzzling objects in the universe. They challenge our understanding of the very nature of space, time, and the fundamental forces of the cosmos. One of the central enigmas surrounding black holes is the information paradox, which has perplexed physicists for decades. The paradox arises from the fact that, according to general relativity, once something crosses the event horizon of a black hole, it can never escape. This suggests that information about the matter falling into the black hole is lost forever. But this directly contradicts a key principle of quantum mechanics, which asserts that information about a system should never be lost, even in the most extreme conditions. So what happens to all the information that falls into a black hole? Does it truly disappear, or is there a deeper explanation? This problem is one of the greatest unresolved issues in modern physics. For many years, scientists, including Stephen Hawking, have grappled with this paradox. Hawking initially proposed that black holes could indeed emit radiation, now known as Hawking radiation, which suggested that black holes might eventually evaporate over time. However, this process raises the same problem. What happens to the information contained within the objects that fall into the black hole? Is it forever lost, or does it somehow get released back into the universe? One intriguing approach to resolving this paradox comes from Raphael Sorkin, who proposed a theory called causal sets in quantum gravity. Sorkin's work challenges the traditional way of thinking about space-time, suggesting that space and time might not be continuous at the smallest scales but rather discrete. In his model, space-time is made up of a causal set of events, each one representing a discrete point in space and time. This idea leads to a different perspective on black holes, particularly the event horizon. Instead of the event horizon being a rigid boundary where information is lost, Sorkin's theory suggests that information might be preserved in the causal set, even if it crosses the event horizon. This could offer a potential resolution to the information paradox, suggesting that while the appearance of a black hole might suggest information is lost, the underlying structure of space-time might actually preserve that information in a way that we haven't yet fully understood. Another alternative theory comes from Daniele Oriti, who has proposed group field theory as a way to unify quantum mechanics and general relativity. Group field theory is a quantum theory of gravity that suggests space-time itself is not a smooth, continuous fabric, but is made up of discrete quantized units. Oriti's theory posits that the structure of space-time at the smaller scales, what we refer to as the Planck scale, may be fundamentally different from what we observe at larger scales. In the context of black holes, Oriti's approach could provide new insights into the nature of the event horizon. Instead of treating it as a strict boundary, Oriti's theory suggests that the event horizon could be a more fluid, dynamic feature of space-time, influenced by the quantum nature of gravity. This could open up new possibilities for understanding how information behaves in the extreme environments of black holes, and might even offer a solution to the paradox of lost information. While these theories challenge our traditional understanding, they are still in the early stages of development. The concept of quantum gravity, which attempts to reconcile the laws of quantum mechanics with the theory of general relativity, is still a work in progress. The dynamics of black holes, especially at their cores, are so extreme that our current tools and theories are not yet sufficient to fully explain them. However, new advancements in theoretical physics and observational techniques could one day allow us to test these theories more rigorously. In the search for answers, Matthew J. Lake, a physicist who has studied the internal structure of black holes, has proposed some innovative thought experiments that challenge existing models of black hole interiors. Lake's work involves studying the behavior of matter and energy inside the event horizon. a region that has traditionally been seen as a one-way ticket to oblivion. According to traditional models, once matter crosses the event horizon, it is doomed, unable to communicate with the outside universe. But Lake's thought experiments propose that, under certain conditions, the internal structure of a black hole could be much more complex than previously imagined. He suggests that black holes may not simply be death traps for matter, but could contain regions where quantum effects allow for the preservation or even transfer of information. This would radically change our understanding of black holes and their role in the universe. While these theories are still speculative, they highlight how little we truly understand about black holes and their place in the cosmos. As we continue to explore the mysteries of these enigmatic objects, we are forced to confront the limits of our current theories and open ourselves to new ideas. The study of black holes has become one of the frontiers of modern physics, a place where the deepest questions about space, time, and the nature of the universe itself are being tested. Perhaps one of the most profound implications of these theories is the possibility that black holes are not just cosmic destroyers, but cosmic gateways, portals that could hold the key to understanding the fundamental nature of reality. The information paradox, for example, may not be a paradox at all, but a hint that our current understanding of the universe is incomplete. Just as the discovery of quantum mechanics revolutionized our view of the microworld, the resolution of the black hole information paradox could force us to rethink our ideas about space, time, and the fundamental structure of the cosmos. As we look deeper into the heart of black holes, we begin to realize that they are not just the endpoints of stars, but rather they may be windows into the very fabric of the universe itself. The questions they raise are some of the most profound we can ask. What happens to information in the most extreme environments? How do quantum mechanics and gravity work together? Or do they? And perhaps most tantalizing of all, could black holes be the key to unlocking the mysteries of dark matter, dark energy, and the very origins of the universe? The journey into the mysteries of black holes is far from over. Every new discovery, every new theory brings us closer to understanding the universe in ways we've never imagined. The paradoxes of black holes challenge us to think beyond our current knowledge, pushing the boundaries of what we know and opening the door to a future where the mysteries of space and time are no longer just questions, but answers waiting to be uncovered. As stars reach the end of their lives, not all of them end in fiery explosions or collapse into the darkness of black holes. For smaller stars, typically with a mass up to about 8 times that of our Sun, their final stages take a different path, leading them to become white dwarfs, small, dense remnants of stars that once shone brightly across the cosmos. The life cycle of these stars follows a peaceful but significant transformation. As they exhaust their nuclear fuel, their cores contract and heat up, while their outer layers expand. Eventually they shed these outer layers, creating a glowing shell of gas and dust known as a planetary nebula. What remains at the center of this nebula is a white dwarf, a stellar remnant that no longer has the fuel to undergo fusion, but continues to glow with the residual heat from its earlier life. White dwarfs are made mostly of carbon and oxygen, the products of nuclear fusion that occurred in the star's core. They're extremely dense, about 1 million times denser than Earth. To give you an idea of just how compact they are, imagine compressing the mass of our Sun into a ball the size of Earth. The gravity at the surface of a white dwarf is so intense that if you were to drop an object from just a few inches above the surface, it would hit the ground at the speed of light. While white dwarfs no longer engage in fusion, they still have a crucial role in the grand scheme of galactic evolution. In fact, their creation and eventual fate are tied to the very process that formed the elements necessary for life as we know it. The formation of white dwarfs is directly linked to the elements that make up our planet, our atmosphere, and our very bodies. The hydrogen and helium from which stars like our Sun are born are fused into heavier elements like carbon and oxygen during their lifetimes. These elements are then released into space when the star sheds its outer layers, enriching the interstellar medium and contributing to the creation of new stars, planets, and even life. This cycle of birth, life, death, and rebirth is integral to the process described by Edward O. Wilson's biophilia hypothesis, which posits that humans have an inherent connection to the natural world, shaped by the elements that form through the life cycles of stars. Wilson's theory suggests that the elements forged in stars are not just the foundation of planets, but are intimately connected to the emergence of life itself. In this sense, white dwarfs, though they may seem like the end of a star's life, are in fact critical to the continuity of life across the universe. But the story doesn't end there. The fate of white dwarfs offers yet another layer of intrigue. Over the course of billions of years, white dwarfs slowly cool and fade away, becoming what are known as black dwarfs, objects that no longer emit light or heat. However, before they reach this ultimate end, some white dwarfs may experience a dramatic event known as a nova, a powerful eruption caused when a white dwarf accretes material from a nearby companion star. This material builds up on the white dwarf's surface until it ignites in a thermonuclear explosion, briefly making the star shine brighter than the entire galaxy it resides in. These nova events play a role in the enrichment of the galaxy, spreading heavy elements into space that can be incorporated into future generations of stars, planets, and life. White dwarfs also serve as an essential part of the larger galactic ecosystem, influencing the formation of new stars and planets. Tamas Budavari, a researcher known for his work on stellar populations within galaxies, has contributed significantly to our understanding of how white dwarfs fit into the galactic evolutionary process. Budavari's work explores how white dwarfs, along with other stellar remnants, affect the overall composition of galaxies. In a sense, they are the quiet guardians of galactic evolution, their slow cooling and eventual transformation into black dwarfs contributing to the long-term evolution of their host galaxies. The cycle of stars, from birth to death to rebirth, is not just a series of isolated events, it is an ongoing process that shapes the very fabric of galaxies. As we look at the broader implications of white dwarfs, their role becomes even more fascinating. These stellar remnants not only contribute to the chemical enrichment of galaxies, but they also offer a glimpse into the future of our own solar system. In about 5 billion years, our Sun will enter its red giant phase, shedding its outer layers and eventually leaving behind a white dwarf. This process will mark the end of our Sun's life, but it will also set the stage for the formation of new stars and planets in the distant future. The Sun's transformation into a white dwarf will be part of a larger cosmic cycle, one that continues to shape the universe long after the star itself has faded. White dwarfs also play a crucial role in the larger context of stellar evolution. As they cool and fade, they may eventually become the seeds of future star systems. Alan Guth's inflationary multiverse theory introduces an exciting speculative view of how white dwarfs might fit into the grander picture of the universe's evolution. Guth, a theoretical physicist known for his work on the early universe and cosmic inflation, proposed that our universe might be part of a much larger multiverse. According to his theory, the death of stars like our Sun, transitioning into white dwarfs, could be part of an ongoing cosmic process in which the formation of new stars and systems is tied to the very structure of the universe itself. Perhaps, in some far future, the cooling remnants of white dwarfs could contribute to the birth of new star systems, continuing the cycle of galactic evolution. In essence, white dwarfs are not just the quiet remains of stars, they are integral to the continued evolution of galaxies and the ongoing cycle of star formation. Their formation, cooling, and eventual transformation into black dwarfs is a process that ties together the past, present, and future of the universe. From their role in enriching the interstellar medium to their potential influence on future star systems, white dwarfs are much more than the end of a star's life. They are part of a much larger cosmic story, one that spans billions of years and shapes the very future of the galaxies they inhabit. As we continue to study white dwarfs and their role in galactic evolution, we are reminded of the interconnectedness of the universe. The elements that make up our world were forged in the hearts of stars, and through the death of stars like our Sun, those elements will continue to shape the cosmos for billions of years to come. White dwarfs are not just remnants. They are part of the ongoing cycle of life, death, and rebirth that defines the universe itself. When we look up at the stars, we often see them shining brightly in the night sky, unaware of the incredible journey they go through, which ultimately leads to their death. But the death of a star is not a simple end. It is an essential part of the universe's larger story. Stellar remnants, white dwarfs, neutron stars, and black holes are the crucial pieces of this story, shaping the future of galaxies and the cosmos itself in ways that are still unfolding. These remnants, born from the fiery deaths of once mighty stars, are far more than just quiet relics of the past. They are active participants in the evolution of the universe. When a star dies, it doesn't disappear entirely. Instead, it leaves behind a remnant that can continue to influence the galaxy around it. White dwarfs, the remnants of lower mass stars, slowly cool and fade over billions of years. Neutron stars born from the death of massive stars are incredibly dense, with gravity so strong that they warp space and time itself. Black holes, the most extreme stellar remnants, continue to captivate our imaginations, with their event horizons pulling in everything that ventures too close. Though these remnants may appear inert, they play vital roles in their galactic environments. Their presence impacts the evolution of their host galaxies, influencing star formation, the distribution of elements, and even the structure of the galactic disk itself. Stellar remnants like white dwarfs contribute to the chemical enrichment of the interstellar medium, spreading elements like carbon, oxygen, and iron, elements essential for the formation of planets and life. The energy released in supernova explosions, which give birth to neutron stars and black holes, scatters these elements far and wide, seeding future generations of stars and planetary systems. However, the role of these remnants goes beyond their influence on the materials that make up future stars and planets. They also play a crucial role in shaping the larger structure of galaxies. Ruth Durrer, a prominent cosmologist, has explored the connection between the cosmological constant, the force that drives the accelerated expansion of the universe, and the presence of stellar remnants. Durrer's work suggests that the energy and dynamics of stellar remnants, particularly black holes, may be tied to the expansion of the universe itself. The immense energy released during the formation of black holes could influence the rate at which galaxies expand and the way matter is distributed throughout the cosmos. The stellar remnants that litter the universe, far from being remnants of the past, may play a central role in the future of galaxy formation, influencing how new stars and systems emerge in the far-flung future. But what if the death of stars and the formation of these remnants is part of an even grander cyclical process that stretches beyond the life of any single universe? Jean-Pierre Luminet, a theoretical physicist and cosmologist, has suggested that stellar remnants could hold the key to understanding the Big Bounce theory, which posits that the universe undergoes cycles of expansion and contraction, rather than being born only once in the Big Bang. According to this theory, each cycle ends in a big crunch, where the universe collapses upon itself and then begins anew with another Big Bang. Luminet speculates that the creation of black holes and other stellar remnants might be linked to this process of cosmic rebirth. If black holes indeed serve as portals to other universes, as some theories suggest, then each stellar death might not just mark the end of a star, but the potential beginning of a new universe, one that could give rise to entirely new cycles of cosmic creation and evolution. This speculative view offers a fascinating twist on the nature of stellar remnants. Rather than simply being the final remnants of dead stars, black holes and other remnants could be seen as a bridge to new universes, continuing the cycle of cosmic birth and death. The idea of stellar remnants playing such a pivotal role in the creation of new universes is still theoretical, but it adds a layer of depth to our understanding of the universe as a whole. It suggests that the universe itself may not be a static, one-time event, but rather a constantly evolving, ever-recycling entity. Even without delving into the idea of alternate universes, the role of stellar remnants in shaping the universe is undeniable. Their influence stretches far beyond their immediate surroundings, affecting not just the evolution of their host galaxies, but the very fabric of the universe itself. These remnants are the sources of the heavy elements that form the building blocks of planets and life, the cosmic engines that power galaxies, and the harbingers of the future, as they may one day contribute to the formation of new stars and systems. One of the most fascinating aspects of stellar remnants is their contribution to the long-term evolution of galaxies. Tamas Budavari, a physicist who has studied stellar populations within galaxies, has explored how the presence of white dwarfs and neutron stars can influence the overall dynamics of a galaxy. His research suggests that stellar remnants may play a significant role in regulating star formation rates within galaxies, potentially acting as cosmic regulators that prevent too much gas from collapsing into new stars. This regulation is critical for maintaining the balance between stellar birth and death, ensuring that galaxies evolve at a steady pace, rather than rushing through their life cycles too quickly. As we look forward in time, it's important to realize that the death of stars and the formation of stellar remnants are not isolated events. They are integral to the ongoing evolution of the universe. The energy released by black holes and neutron stars, the heavy elements scattered by supernovae, and the cooling of white dwarfs are all part of a continuous process that shapes the galaxies and systems that will follow. The death of stars does not signal the end of the universe. It is a vital step in the ongoing cosmic dance, ensuring that new stars, planets, and perhaps even life will continue to emerge. In the grand scheme of things, stellar remnants are not just the final chapters of a star's life. They are the seeds of future stars, planets, and galaxies. They are the cosmic recyclers, ensuring that the materials created in stars' fiery cores continue to be redistributed across the universe, enriching future generations of stars and systems. From regulating star formation in galaxies to potentially opening doors to new universes, the death of stars is an essential ongoing process that shapes the future of the cosmos. Far from marking an end, stellar death is the beginning of the next chapter in the ever-evolving universe, where every final breath of a star gives rise to the infinite possibilities of creation. When a massive star collapses, it doesn't just end with a brilliant explosion or a quiet fade into the cosmos. It sends ripples through the very fabric of space-time, ripples known as gravitational waves. These waves, created by the acceleration of massive objects like collapsing stars or merging black holes, spread outward across the universe at the speed of light, carrying with them crucial information about the most extreme events in the cosmos. Gravitational waves allow us to hear the universe in a way we've never been able to before, offering a new, deeper insight into the lives and deaths of stars. Gravitational waves were first predicted by Albert Einstein in his theory of general relativity, which described how massive objects warp the fabric of space and time. Just as a stone thrown into a pond creates ripples on the surface of the water, massive objects like stars and black holes create ripples in space-time as they accelerate. When these ripples pass through Earth, they stretch and squeeze space itself, causing tiny but measurable changes in distance. These changes are incredibly small, far smaller than the width of a proton, but they carry the signature of the cosmic event that created them. The breakthrough in detecting gravitational waves came in 2015, when the Laser Interferometer Gravitational Wave Observatory, or LIGO, made the first successful detection of these waves. The waves they detected were the result of two black holes merging, a cataclysmic event that sent out gravitational ripples across the universe. This discovery opened an entirely new chapter in our understanding of the cosmos, confirming Einstein's century-old prediction and proving that we could observe some of the most violent and extreme events in the universe by listening to the space-time distortions they created. Kip Thorne, one of the leading scientists behind LIGO, was instrumental in the design and development of the observatory. His work on the theoretical foundations of gravitational waves and his contributions to the detection of these waves have had a profound impact on our understanding of the universe. Thorne's work demonstrated that the collision of massive objects, such as black holes or neutron stars, could create gravitational waves strong enough to be detected on Earth. His contributions to LIGO's success were pivotal, and in 2017, Thorne was awarded the Nobel Prize in Physics, alongside Rainer Weiss and Barry C. Barish, for their groundbreaking work. However, detecting gravitational waves is not just about observing the latest cataclysmic events. The waves from stellar collapse and the merging of compact objects also provide us with a way to look back in time. Michael K. Hines, a physicist exploring the propagation of gravitational waves, has proposed an alternative model for how these waves move through the dense regions of the galaxy. Hines suggests that gravitational waves, as they travel through different galactic environments, can be influenced by the dense interstellar medium, altering their shape and strength. This opens the possibility that by studying the ways in which gravitational waves interact with different cosmic environments, we could gain a deeper understanding of galactic structure, star formation, and even the distribution of dark matter. But it's not just about detecting events in the here and now. Gravitational waves may also provide a window into the past. Andreas K. H. Emby, another physicist working in the field of gravitational wave astronomy, has speculated that the detection of ancient stellar collapse events could help us understand the distribution of dark matter throughout the universe. Dark matter, which makes up about 25% of the universe's total mass, is invisible to traditional telescopes because it doesn't emit light. However, its presence can be inferred by its gravitational effects on visible matter. If gravitational waves from ancient stellar collapses, particularly those from stars in the early universe, can be detected, they could provide new insights into the distribution of dark matter across cosmic time. The idea that gravitational waves could help us detect dark matter is speculative, but it highlights the broader potential of this new field of astronomy. Instead of only looking at light from distant stars and galaxies, we can now listen to the universe in a completely different way. Gravitational waves allow us to probe the most energetic and mysterious events in the universe. Events that might otherwise be hidden from us. Whether it's the merger of two black holes, the collapse of a massive star into a neutron star, or the effects of dark matter on the propagation of gravitational waves, each new detection opens up new possibilities for understanding the cosmos. In addition to their role in unveiling cosmic mysteries, gravitational waves also offer a unique way to study the structure of black holes and neutron stars. Rainer Weiss, another key figure behind LIGO, contributed significantly to the development of interferometry, a technique that allows us to measure incredibly small changes in distance. This technique is at the heart of LIGO's ability to detect gravitational waves. By measuring the tiny shifts in distance caused by gravitational waves, scientists can now observe the properties of black holes and neutron stars in ways that were once impossible. For example, gravitational waves from a black hole merger can reveal details about the size, spin, and even the internal structure of these mysterious objects. One of the most exciting aspects of gravitational wave astronomy is the possibility of using it to study the most extreme and distant events in the universe. As gravitational waves travel across vast distances, they carry with them information about the events that created them. Unlike light, which can be blocked or absorbed by dust and gas, gravitational waves can travel freely through the universe, unimpeded by obstacles. This means that gravitational waves can provide us with a direct view of the universe's most distant corners, including events that occurred billions of years ago. For instance, as LIGO and other gravitational wave observatories continue to detect these waves, we may begin to gather data about the very first stars and black holes that formed after the Big Bang. By studying these early cosmic events, we could gain insight into the formation of galaxies and the evolution of the universe itself. Each new detection of gravitational waves is a piece of the puzzle, allowing us to probe the universe's deepest mysteries and unlock the secrets of its earliest moments. In the end, gravitational wave astronomy is not just a new tool for studying stellar collapse and black hole mergers, it's a completely new way of observing the universe. As we continue to detect these ripples in space-time, we open up an entirely new realm of discovery, one that could forever change our understanding of the cosmos. From probing dark matter to studying the births and deaths of stars, gravitational waves offer a fresh and exciting perspective on the universe, revealing the hidden forces at work beneath the surface of space and time. The life and death of stars form one of the most awe-inspiring cycles in the universe. It's a never-ending process of creation, destruction, and rebirth, a cosmic rhythm that has shaped the very fabric of galaxies, star systems, and perhaps even life itself. When a star dies, it doesn't simply vanish, it transforms, leaving behind remnants that continue to influence the universe long after its light has faded. The death of a star is a pivotal moment in the ongoing evolution of the cosmos, setting the stage for the birth of new stars, planets, and even the molecules that might one day give rise to life. The life cycle of a star is deeply interconnected with the universe's broader cycle. Stars are born from clouds of gas and dust, their energy fueled by nuclear fusion. But as they age and burn through their fuel, they eventually reach a point where they can no longer sustain the pressure needed to counteract the force of gravity. The result is the death of the star, which can take many forms depending on its mass. A small star like our Sun becomes a white dwarf, while a more massive star may end its life in a supernova explosion, leaving behind either a neutron star or a black hole. Yet, while the death of a star might seem like the end, it is actually the beginning of something new. Nathalie Darreguel, a physicist known for her work in cosmology, proposed the concept of stellar archaeology, a fascinating theory that looks at the death of stars as a way of understanding the larger evolutionary history of galaxies and star systems. Darreguel's theory suggests that the processes by which stars die, through supernova, the shedding of their outer layers, or the collapse into black holes, are not simply random events. Instead, they contribute to the creation of the very building blocks that will form future stars, planets, and even life. When a star dies, it releases enormous amounts of energy and materials into the surrounding space. These elements, particularly heavier elements like carbon, oxygen, and iron, are scattered into the interstellar medium, enriching the gas and dust clouds from which new stars will form. This stellar fertilization creates a rich tapestry of material that will eventually coalesce into new stars, potentially even forming the conditions for life. The heavy elements that make up the planets we live on were once forged in the hearts of ancient stars, making the death of one star a crucial step in the creation of the next generation. This idea of death as creation is not just a scientific observation. It carries deep philosophical implications about the interconnectedness of all things in the universe. David Bohm, a renowned theoretical physicist, developed an interpretation of quantum mechanics that emphasized the fundamental interconnectedness of the universe. Bohm's holistic view of the cosmos suggests that everything is interconnected, that nothing exists in isolation. In this view, the death of a star is not a solitary event, but part of a much larger, ongoing process of transformation. The energy and elements released during a star's death become part of the greater cosmic web, influencing everything from the formation of new stars to the creation of planets and even life. In this sense, the death of a star is a profound act of cosmic recycling, a necessary step in the ongoing evolution of the universe. The cycle of death and rebirth extends beyond the realm of stars to the larger structure of the cosmos itself. Stars are not isolated points of light in a vast, empty universe. They are part of galaxies, which are in turn part of an even larger cosmic structure. As stars die and release their elements into space, they enrich the interstellar medium, contributing to the formation of new stars and galaxies. In a sense, the death of individual stars is tied to the broader evolutionary process of galaxies themselves. New generations of stars are born from the ashes of their predecessors, and the cycle of stellar life and death continues. This cyclical nature of the universe also ties into broader ideas about the fate of the cosmos. The death of stars and the formation of stellar remnants such as white dwarfs, neutron stars, and black holes can help us understand not just the evolution of galaxies, but the future of the universe itself. If we take into account the Big Bang theory and the expansion of the universe, we are reminded that the universe, like the stars within it, is constantly evolving. The death of stars contributes to this ongoing transformation, ensuring that the universe remains dynamic, ever-changing, and ever-creating. One of the most fascinating aspects of this cosmic cycle is how it links the smallest scales of matter to the larger scales of the universe. The death of a star may seem like a small event in the vastness of the cosmos, but it is intricately tied to the future of everything. As stars explode in supernovae or collapse into black holes, they reshape the fabric of the galaxy, creating the conditions for new stars to form. The elements they release into space eventually become the building blocks for planets, and possibly life itself. Even the mysterious dark matter, which makes up a significant portion of the universe's mass, may have some connection to the processes that occur during stellar death, further highlighting the interconnected nature of the cosmos. The cycle of stellar life and death also offers us a glimpse into the future. The elements created in stars are not just the foundation for life as we know it. They are the materials from which future civilizations might arise. The same elements that make up our bodies were forged in the hearts of ancient stars, and the same cosmic processes that created us will one day shape the future of the universe. In this sense, the death of stars is not a final end, but a new beginning, a step in the ongoing process of cosmic evolution. Ultimately, the death of a star is far from final. It is a necessary part of the universe's ongoing transformation. The materials released during stellar death create the conditions for new stars, planets, and galaxies to form. These remnants, though they may seem like the end of a star's life, are actually the seeds of new creation. The interconnectedness of all things in the universe, whether it's the birth of stars, the creation of elements, or the evolution of galaxies, reminds us that the death of a star is not an isolated event, but part of a much larger ongoing cycle of life and death, creation and destruction that defines the cosmos. The universe, in its infinite complexity, is a never-ending process of transformation, and the death of stars plays a critical role in that cycle. Each star, as it lives and dies, contributes to the ongoing evolution of the cosmos, ensuring that the story of the universe continues. In this cosmic cycle, there is no true end, only a continuous flow of creation and change, where each death is a step towards something new, something even greater. Just as the stars themselves are born from the remnants of past generations, so too does the universe evolve, ever transforming, ever creating, ever alive. As we look to the distant future of the universe, the stars that light up our night sky today will eventually fade away. Their deaths are not just individual endings, but markers in the long and inexorable journey toward the ultimate fate of the cosmos. The question is, what happens when all the stars have burned out, when the universe becomes too cold and dark for new stars to form? What lies ahead for the remnants of these stars and for the universe as a whole as it cools and ages over the course of billions and billions of years? One possibility is that the universe will enter what scientists call the Dark Age, a time when all the stars that currently light the cosmos have exhausted their fuel and no new stars are born. Theodore K.M. Nguyen, a physicist, has developed models to describe this eventual cooling of the universe. According to his work, as the stars burn out, galaxies will become dark and lifeless, with only the remnants of stars, white dwarfs, neutron stars and black holes remaining. This dark age would be a time when the universe, bereft of the energy needed to form new stars, becomes increasingly cold and empty. The once vibrant and active universe, filled with the fiery brilliance of stars, would slowly fade into darkness. This scenario, however, is far from an immediate future. The process of the universe cooling is gradual, taking place over an incomprehensibly long timescale. The final death throes of the stars would stretch across billions of years, with each generation of stars gradually burning out. White dwarfs would cool and dim over time, turning into cold, dark remnants. Neutron stars, too, would slowly radiate their remaining heat into space, eventually becoming dark and silent. And black holes, which are often the ultimate fate of the most massive stars, would continue to exist, but even they are not immune to the inexorable march of time. Over even longer periods, black holes would slowly lose mass through the emission of Hawking radiation, eventually evaporating into nothingness. But what happens after this? Is the universe doomed to an eternal empty dark age? Some scientists speculate that this long period of cosmic quiet might not be the end of everything, but simply another phase in an ongoing cycle of cosmic evolution. One idea comes from James Hartle, a theoretical physicist who proposed the no-boundary condition. This theory suggests that the universe, at its very beginning, may not have had a distinct boundary. Instead, it may have arisen from a quantum state without any sharp separation between space and time. Essentially, the universe could have begun without any definite edge. Extending this idea to the far future, Hartle's theory suggests that as the universe cools and decays, it could eventually reach a point where space and time themselves break down. Matter and energy could be converted into dark energy, which is thought to be responsible for the accelerated expansion of the universe. This conversion could lead to a new phase in the universe's evolution, one in which space-time itself behaves in ways that are radically different from anything we experience now. While these ideas are still highly speculative, they open the door to the possibility that the end of stars might not mark the absolute end of the universe itself. Instead, it might lead to a new kind of universe, one shaped by dark energy and governed by principles of physics that we are only beginning to understand. The universe, it seems, might be capable of cycling through phases of expansion, cooling, and perhaps even rebirth in ways that challenge our conventional ideas of what an end might look like. In addition to these ideas about the cooling of the universe and the potential for new phases of cosmic evolution, Brian Greene, a theoretical physicist known for his work on string theory and the multiverse, has proposed that the death of stars could be part of a much larger cosmic picture. Greene's work suggests that the universe we observe may be just one of many in a vast multiverse, where different universes exist with varying physical laws and constants. If this idea is correct, then the death of stars in our universe could be part of a grander, ongoing cosmic process that stretches across multiple universes, each undergoing its own cycle of birth, life, and death. This speculative view suggests that while our universe may reach the end of its life in a cold, dark state, the multiverse as a whole may continue to evolve, with new universes being born and dying in a never-ending cycle. The concept of the multiverse adds another layer of complexity to our understanding of the universe's future. If stars die and the universe cools, could the remnants of this universe eventually give birth to new universes in a manner similar to the birth of stars? In the framework of the multiverse, The death of stars in our universe might not be an isolated event, but could serve as part of a larger, ongoing process of cosmic evolution that extends beyond our universe. The death of stars might be one chapter in an ongoing story that spans the life cycles of countless universes, each contributing to the creation of new ones. As we consider the fate of stars and the ultimate end of the universe, we are left with more questions than answers. What will happen when all the stars have burned out? Will the universe continue to evolve in ways we can't yet predict? And if the universe does enter a dark age, can we even begin to comprehend what that future will look like? Theories like those of Nguyen, Hartley and Green offer fascinating glimpses into possible futures for the universe, but they also reveal how much we still don't know about the ultimate fate of everything. Perhaps the most profound realization is that the death of stars, far from being an isolated event, is a necessary part of the ongoing transformation of the cosmos. The elements that are forged in stars and scattered into space during their death are the very building blocks for new stars, planets, and potentially life. Even as the stars fade and the universe cools, they continue to play a critical role in shaping the future. The energy that once powered them may dissipate, but the material they leave behind will continue to influence the universe for billions of years. In the end, the fate of stars is intricately tied to the broader fate of the universe itself. The cooling of the universe, the transformation of matter into dark energy, and the speculative idea of the multiverse all point to a future that is not fixed but continually evolving. Just as stars live, die, and give birth to new systems, the universe may be part of a larger cosmic cycle, one that stretches across unimaginable timescales, where death is not the final end but a precursor to new beginnings. As we peer into the future of stars and the universe, we are reminded that even in the darkest times there is always the potential for renewal, for creation, and for transformation. The journey of a star, from its birth in the swirling clouds of gas and dust to its final moments in the cosmic expanse, is a profound cycle that defines the very fabric of the universe. It is a process of transformation, where death is not an end but a necessary step in the ongoing evolution of galaxies, stars, and planets. The cycle of stellar life and death is a cosmic rhythm, a dance that spans billions of years and has profound implications for the structure of the universe and the emergence of life itself. Stars are born from the cold, dark clouds of hydrogen gas and dust that float through space. Under the force of gravity, these clouds collapse inward, and as they do, they heat up, eventually igniting nuclear fusion in their cores. This process marks the birth of a new star. The energy produced by fusion creates an outward pressure that counteracts the inward pull of gravity, allowing the star to remain stable for millions to billions of years. During this time, the star shines brightly, creating the light and energy that make life possible on planets like our own. The life of a star is a process of constant transformation, as it fuses lighter elements like hydrogen into heavier ones like helium, and then into even heavier elements as the star ages. But just as every birth has its inevitable end, so too does every star. When a star runs out of fuel, it can no longer support itself against the force of gravity, and its core begins to collapse. Depending on the mass of the star, this collapse can take many forms. Smaller stars like our Sun will puff up into red giants before shedding their outer layers and leaving behind a white dwarf. Larger stars will explode in a dramatic supernova, creating neutron stars or black holes in the process. These stellar deaths are violent events, but they are not final. The material released by a dying star enriches the surrounding space, creating the building blocks for new stars, planets, and perhaps life itself. Natalie Darrigal, a physicist, introduced the concept of stellar archaeology, a theory that views the death of stars not as an isolated event, but as part of a larger, interconnected cycle of creation and destruction. Darrigal's theory suggests that the elements and materials created in the cores of stars and released during their deaths are not lost but are repurposed to form the next generation of stars. When a star explodes in a supernova, the elements it has created, elements like carbon, oxygen, and iron, are scattered into space, enriching the gas and dust clouds from which new stars will form. This process, known as stellar fertilization, creates the conditions for the formation of new stars and planetary systems. The cycle of stellar life and death, in this sense, is a continuous process of transformation and renewal, where the death of one generation of stars becomes the seed for the next. This idea of stars as the architects of the cosmos, creating and reshaping the universe with every death, leads us to a broader philosophical consideration about the interconnectedness of all things in the universe. David Bohm, a theoretical physicist known for his work in quantum mechanics, proposed that the universe is an interconnected whole, a web of relationships where everything is connected and nothing exists in isolation. Bohm's view of the universe suggests that the life and death of stars is not a series of random independent events, but rather part of a larger unified process. Stars are not just individual objects, they are interconnected with the very fabric of space-time itself, influencing and shaping the universe around them. In Bohm's view, every star, every planet, every particle of matter is a reflection of the whole, the universe as a dynamic, interconnected system. The death of a star, then, is not just the end of one star's life, but a part of the ongoing transformation of the cosmos. The energy released in a supernova, the elements scattered into the interstellar medium, and the remnants left behind, all of these contribute to the ongoing cycle of cosmic evolution. The material created in stars forms the building blocks for new stars, new planets, and even new forms of life, suggesting that the universe is always in a state of becoming, always evolving and transforming. This perspective, which sees the death of stars as part of a larger cosmic process, challenges the traditional view of the universe as a static, unchanging entity. Instead, it paints a picture of the cosmos as a dynamic, ever-evolving system, where each star, each galaxy, and each individual life is part of an ongoing cycle of creation, death, and rebirth. The universe, in this sense, is a continuous flow of energy and matter, always in motion, always changing, always becoming. As we reflect on the cycle of stellar life and death, we realize that stars are not just distant, isolated objects. They are the very engines of cosmic evolution. Their birth, their life, and their death are all part of a larger process that shapes the universe and gives rise to everything we know. The death of a star, far from being an end, is a necessary step in the creation of new stars, planets, and potentially life. The elements forged in stars, scattered into the universe during their deaths, are the raw materials from which the future will be built. In this sense, the death of stars is not a final tragedy, but a part of the ongoing, infinite transformation of the universe. In the grandest view of all, the circle of life in the cosmos is a never-ending process of creation, destruction, and renewal. The death of one generation of stars is followed by the birth of the next, each generation contributing to the ongoing evolution of the universe. Every death, every transformation, every cycle is part of the cosmic flow, a flow that has been unfolding for billions of years and will continue to unfold for billions more. And through it all, the elements forged in the hearts of stars, elements like carbon, oxygen, and iron, are the very building blocks of life itself, ensuring that the cycle of life and death in the cosmos continues eternally and endlessly in an infinite dance of creation. As we look to the stars, we are reminded that the death of a star is not the end. It is a pivotal moment in the ongoing story of the universe. Stars are born, live, and die, and their deaths fuel the creation of the next generation of stars, planets, and potentially life itself. It is a cycle that has been unfolding for billions of years and will continue for billions more, a cycle that shapes the universe and its evolution. Yet, even as we observe this cycle, we must acknowledge that it's only one chapter in the larger, incomprehensible story of the cosmos. Beyond the stars, there are mysteries that still elude us, puzzles that challenge the limits of our understanding and push the boundaries of science. One of the biggest of these mysteries is dark matter, the invisible substance that makes up a significant portion of the universe's mass. Despite years of searching, we still don't know what dark matter is. We know it exists because of its gravitational effects on visible matter, but it doesn't interact with light, making it nearly impossible to detect directly, and yet its presence is undeniable. The discovery of dark matter is just one of the many unknowns in the universe that fuels the curiosity and imagination of scientists around the world. Then there is the idea of the multiverse, a concept that has sparked intense debate and speculation. Some scientists, like Max Tegmark, have proposed that our universe might be just one of many in a vast multiverse. According to this idea, each universe could have its own set of physical laws and constants, making the multiverse an infinite landscape of possibilities. While the multiverse theory is still largely speculative, it raises intriguing questions about the nature of reality. Could there be universes where the laws of physics are entirely different from our own? Could life exist in forms we can't even imagine? The multiverse theory, if true, would redefine our understanding of existence and our place in the cosmos. And of course, we must consider the ultimate fate of the universe itself. Will it continue to expand forever, growing colder and darker as stars burn out and galaxies drift apart? Or is there some larger cosmic cycle at play, a process of creation, destruction, and rebirth, where the universe will eventually collapse and then begin anew? Some theories, like the Big Crunch, suggest that the universe may eventually collapse in on itself, leading to a new Big Bang and the birth of a new universe. Others, like the Big Rip, speculate that the expansion of the universe will accelerate, eventually tearing everything apart. Still, other theories, like those proposed by James Hartle and Stephen Hawking, suggest that the universe might not have a beginning or an end, but instead is part of an eternal cycle, where time and space themselves behave in ways we can barely comprehend. As we contemplate these possibilities, we are reminded of how little we truly know about the universe. The stars we see shining in the night sky are only a small part of a much larger story, one that stretches back to the very beginning of time and continues to unfold in ways that challenge our understanding of reality. The death of stars, the mysteries of dark matter, and the possibility of the multiverse all point to a universe that is far more complex and mysterious than we could have ever imagined. Yet, even in the face of these unknowns, there is something deeply humbling and awe-inspiring about the journey of a star. It is a journey that mirrors our own, one of creation, transformation, and eventual dissolution. The atoms in our bodies, the very elements that make up life, were forged in the hearts of stars. We are not separate from the universe. We are woven into it, connected to the stars and their cycle of life and death. As the stars live and die, so too does the universe evolve, and we are all part of that ongoing transformation. In the end, the death of stars is not just about the end of one cycle, but the beginning of another. It is a reminder that life and death are not opposites, but parts of the same eternal cycle, a cycle that defines the cosmos and gives it meaning. The universe, in all its vastness and mystery, is constantly changing, constantly evolving, and we too are part of that cosmic journey. As we look to the stars, we're reminded that we're not just observers of the universe, we are participants in it, woven into the fabric of existence in ways that we are only beginning to understand. The journey of the stars is far from over, and as we continue to explore the mysteries of the cosmos, we're drawn ever deeper into the grand unfolding story of life, death, and rebirth.